the previous lecture we were discussing about input resistance of the op amp, and we had shown how to compute the input resistance, and also we had discussed what are the errors associated with the input resistance and so on, and we also had given an example with respect to pH measurement. So, in this class we discuss about output resistance of the op amp and the errors associated with the output resistance, and then how to tackle this output resistance issues in the op amp. This output resistance also an important issue which often ignored by the by most of the designers. So, today we discuss about output resistance of the op amp. The first thing is that conventionally they think that the output resistance of the op amp, which I call as R0, output resistance of the op amp, that conventionally it is taken as 0, but actually it is not 0. This is the thing that we want to say, that is output resistance of the op amp is not 0. Of the op amp is not 0, and the second point is it varies with the gain. It varies with the gain, because even for a given op amp the output resistance is not 0 and also it is not constant, it varies with the gain, and this must be understood actually clearly, and the changes that is coming because of that to be applied carefully. So, let us see what is the what you mean output resistance first, because we want, before getting into what is the output resistance of op amp, let us see what is the output resistance. Because if I have a source, for example, if I have a source, now we have a resistance here, we call this as a internal resistance. For example, this is a battery, it has its own internal resistance. Now, this battery is a source now, say 12 volt. So, battery source, it has its internal resistance, and then I have a load here. Now, if I look at the voltage across this, that is the what is the voltage across this, this voltage is actually not 12 volt, this V is not equal to 12 volt, because there is a current I in this, that current actually goes through this internal resistance R, I call this a small r. So, there is a voltage drop on the internal resistance. So, voltage drop on the internal resistance R is equal to R into I, because I is the current that is flowing. So, if I take I is the current, then the internal voltage drop is V R into I. So, the output load voltage is load voltage is 12 volt minus R into I. So, output voltage actually changes with the load, that depends upon what is the internal resistance of the internal resistance R of the battery. So, output, because when I changes, then when I changes, then load voltage, that is we call V load is equal to 12 minus R into I. Then with the current, the load voltage changes. So, with current, with load current output load voltage changes. In this case, we have taken a battery and R is taken as the internal resistance. Now, this is true for any source, because if not only for the battery. For example, if I take operation amplifier, then we take operation amplifier, then we have say some input voltage and then some I given some input voltage here, then I get the output voltage here V I V0, and then the output voltage, if I change the load here, I change the load here, this output voltage changes, V0 changes, that is output voltage, output voltage of the op amp changes with the load resistance. Now, the this is because we have to draw the equivalent circuit as this, that is we have op amp is a voltage source, that I put this here like this is a voltage source, that voltage source has its own internal resistance, and that is the internal resistance there, and that is the load, this is the load, this is the load, and this is the equivalent internal resistance, say R0. This is the output voltage that is supposed to be present at the output, this is the V0, and this is the actual voltage that is supposed to come across the load. So, similar to the discussion that we had earlier, that in the case of battery we had an internal resistance R naught, here also the op amp also has its own internal resistance, and then when you change the load, then the voltage across this will change depending upon the internal resistance that it is having. So, this is true for any voltage source, for any voltage source, any voltage source there is a finite internal resistance, So, output voltage will change with the load, The same thing happens in the op amp. The question is how much is the change. So, for in the case of op amp, what is R naught internal resistance, that is the question actually, and then why it should change with the load, and also it changes with the gain, and what is R0. So, we look at this, we can see this carefully in the following manner. What we can do is we take operation amplifier, then I apply some input voltage, assume I give some gain G, and assume it has its known internal resistance, connect to this, then that is the output voltage. Then assume that I have a load here, this is a load, assume this resistance say RF R1 are very high, that is there is no essentially not much current is flowing, negligible current is flowing through RF and R1, assuming RF and R1 are large, very large, we can assume are not large, we can take it as take I as the actual current, I as the full current of op amp. So, we assume that the I is the full current of the operation amplifier. Now, if you look at the operation amplifier, what is the actual resistance involved inside this R? There is a because it is acting as a source, it has its own resistance. This actually, if you look at our earlier op amp circuit, that we have this, for example, in this case our classical op amp circuit, if we take, this is V 0. Now, for example, this resistance will be the output resistance of the op amp, because we give here plus 15 and minus 15 volt, and we have of course, assume that I give you some input voltage here. Then the output, in this case uh, the low, this resistance R, the resistance R is acting as a internal resistance. But the output volt, if I load this one, this is a load, the output load, in this case R acting as an internal resistance, but the effective output resistance, output resistance is not R. This is because, suppose if I load this, if this voltage changes, then effectively, so for example, if I load this, then if this voltage decreases, then this voltage also will decrease, this also will decrease, and that this voltage also will decrease. Then since this is this decreased, and relatively so this current will increase. So, if this decreases and this decreases, and it increase this current, and that will increase the output voltage. Because of the feedback, op amp compensates most of the voltage loss that is taking place because of the current flowing in the internal resistance R. So, the effective output resistance is not really R, it is much smaller than the R. This is because you have a current I flowing here, then we expect R into I is the voltage drop. But then that reduction in voltage, that the current flowing through this reduces the voltage here, that reduces the voltage at this point, and that makes more current flow here, and more voltage appears here to compensate. So, most of the loss that is taking place on the internal resistance of the op amp is compensated because of the feedback action. Because of the closed feedback action, most of the loss is compensated. Because of the closed loop feedback, most of the voltage that is lost is compensated, but not fully, but most of the voltage that we have lost is put back because of the feedback action. This is because of the closed loop feedback action. That is the reason that effective resistance is not R, it is much smaller than R. So, the effective resistance, the effective output resistance, is much smaller than R. This is because of the closed loop feedback. So, the same thing happens in the case of operation amplifier also. So, if I have the circuit here, then if I give the input voltage and if I put the load here, then if I change the load here, then current flowing through this changes I, and then the current flowing through this also I. So, voltage across this, the voltage drop across this resistance also changes, voltage drop changes. When the voltage across this changes, then we expect the output voltage to change here. Then when the output voltage changes, that change is reflected here and that corrects it back, that basically it increases this voltage. For example, if I increase the current I, then the voltage decreases here, that decreases the voltage here and that increases this voltage such that this voltage is put back to the original value. So that the loss in the internal resistance is partly compensated. So, effectively you see very small change in the output voltage due to the current change, this is because of the feedback. So, effectively we say the effective output voltage change is the effective output voltage change is much smaller. This we represent with a new internal resistance, the effective internal resistance. So, and then we call this effective output voltage change as much smaller, that is equal to R 0 into I, where we call R 0 is the effective internal resistance, or simply we call output resistance of the op amp, where R 0 is uh, um, effective output resistance of the op amp. Where R 0 is much smaller than R. For example, in a typical op amp, circuit, in a typical op amp circuit, R actually equal to around 100 ohms, but R 0 is few milliohms. So, this computation is not difficult, that we can really do that, assuming that the current I is the output current. Then if I is the output current, then I can find out what is the voltage drop here, that would be R into I. But then we know that this voltage is not, the change here is not R into I, because this change, whatever, if that much change occurs, then that will change this voltage and immediately this will be increased, and again this will try to come back to the original value. But then we know that without load this voltage is less, with load this voltage have to increase, because suppose if I reduce the resistance, the current will increase, that increase in current actually increase the voltage here, that will actually reduce the voltage here, then that will reduce the voltage, that will increase this voltage. So, eventually this voltage will be increased to get back this, but then this increase takes place because there is a decrease in voltage here and there is a decrease in voltage here. So, eventually voltage at this point, if I look at the voltage at this point with and without this load, then you will find with load the voltage at this point, say I call it is in non-inverting terminal, the inverting terminal. So, at inverting terminal the voltage you have to decrease with load. So, in the typical op amp it is around 100 ohms. For example, if I have about 10 milliampere current flowing here through this, then 100 ohm into 10 milliampere, that will give you about 1 volt drop across this. That means, if it is originally 10 volt, it will drop to 9 volt, then this voltage will decrease, that will make this voltage to go up to close to 11, and then this you will get back to 10. That is what in real life happens. So, in real life when the in real life when load resistance is decreased, the the voltage at the inverting terminal decreases so that output voltage uh, is put back. So, that means assume that the voltage change at put back, but there will be some voltage, but output voltage will not be equal to the original value. So, but output voltage will not be equal to original value, because output voltage, if the voltage at inverting terminal have to change, then output voltage also have to change, because output voltage change only changes the voltage at the inverting terminal. So, when you load the op amp, this voltage have to change and that also have to change, and this voltage have to increase. So, this is what happens, but some small change in output is expected. So, if we can write the equation for this, then we can write we can quantify what is the change that is expected, and then we can also write down what is the expected output voltage change. So, we assume that current is high and actual resistance of the op amp is R. So, voltage drop on the internal resistance of the op amp. Op amp is equal to R into I. This is because the current had to go through the internal resistance. Assume the effective output resistance is is R0. This is after compensation, the effective output resistance R0, that is R0 into I is the output voltage change with the feedback, with everything, that if I load with the current I, then output of the op amp changes by this much amount, then I take that R0 as a output resistance equal to output voltage change, because that is how the internal resistance is defined, that is if the output voltage change must be equal to R0 into I. So, R0 is the effective output resistance, I is the load current. So, effective output resistance is R0. So, output voltage change is I. So, we now got the output voltage change, which is R0 into I. If the output voltage changes, then what is the voltage change at the inverting terminal of the op amp? So, what is the voltage change at the inverting terminal of the op amp? That actually that's actually divided by gain, because whatever voltage change that is happening at the output of the op amp, that should be reflected to the inverting terminal. So, we have the gain resistance here. So, whatever change that is taking place here, that have to make a change here by the gain times. So, if, so what the voltage change at negative input is R0 I divided by G, because G is the closed loop gain. So, because if you find that that this voltage divided by the ratio of these two resistors, because output voltage divided by the ratio of these resistance, which is nothing but a gain. So, the output, the voltage change at minus terminal is R0 I by G. So, where G is the closed loop gain. G is the closed loop gain. Now, so we got a voltage change at the inverting terminal. If the inverting terminal voltage changes this much R0 I by G, then what is the change at the output? Because we can find if the minus terminal change occurs by R0 I by G, then output had change by AD, because in any in a op amp the difference between these two voltages amplified by the open loop gain is the output voltage. So, if this point changes by some x, then output will change by x into AD. So, where G is the open loop gain. Now, next question is what is the relation between change at the minus terminal and the change at the output. So, between change in voltage at minus negative terminal and at output terminal. That is actually change at inverting terminal into A is output voltage change. Because the change here that has to happen at the output. So, I can write like this. So, if I take R as the output, then R into I is the change that is taking place at the we have written down already this one, that is output voltage change, that is actually equal to R0 into I divided by G, that is the input voltage the negative terminal change into A, because the A is the open loop gain, and this term gives what is the change at the minus terminal, and that multiplied by the A gives you the output voltage change actually. So, that is the actual voltage drop across the op amp's internal resistance. So, now if we remove I, then you will get that R actually coming as R0 A by G, where R0 is coming as a output resistance. So, if I can write that one, change this one, that comes R into G by A. So, output resistance is related by closed loop gain and open loop gain. So, output resistance R naught R into G by A. R for example, for most of the op amp R is equal to 100 ohms. So, what is R naught comes, for example, if it is 100 ohms, and if I have a gain of 100 G 100 and open loop gain of 20,000, this is open loop gain. this is closed loop gain. And this is the internal resistance of the op amp. So, that actually if you compute this, it comes. So, R naught actually comes, you have 10 power 4 divided by 2 into 10 power 4, that comes 0.5 ohms. 0.5 ohms. So, that is the output resistance of op amp, it is not 0. Now, this is actually for the 741 we have taken typical values, because for 741 the typical value is this is around 100 ohms, and then we are given 100 gain and open loop gain is around 20,000. For same 741, for example, if I give a unity gain voltage follower, for voltage follower for 741, for voltage follower, R naught actually is becoming 100 into 1 divided by 20,000, which actually makes 1 by 200, that is equal to 5 milliohms. So, when the gain is when the closed loop gain is less, then the output impedance also comes down. When the closed loop gain is low, then output when the closed loop gain is low, gain is less, then the output resistance also low. Also low. That is why voltage follower gives the lowest resistance. So, voltage follower gives lowest output resistance. Similarly, we had seen earlier, if the gain is less, the input resistance also less, that is the closed loop gain is less, the input resistance also very high. So, if I have a voltage follower, then this has lowest output resistance and highest input resistance. So, this must voltage follower gives highest input resistance, then second one is the voltage follower gives you the lowest output resistance. Gives lowest output resistance. Because this one have to realize, because that is why very often at the input stage we use voltage follower to get highest input resistance, and then also it gives you the lowest output resistance. And if you increase the gain, then the output resistance will go up. For example, if I take 741 and I try to find out what is R naught for say 1000 gain, then if it is 100 ohms is the internal resistance, and if I go for 1000 gain and with the 20,000 closed loop gain, you will have 5 ohm as output resistance. For 1000 gain, for G is equal to 1000, then output resistance goes up to 5 ohms. This is very large actually. So, one should not think that always output resistance of the op amp is close to 0 and it is constant. It can be very high if you try to get more gain, and what kind of error that then this output resistance gives. because we had seen that output resistance of the op amp is not 0 and it varies with the gain. If you want highest gain, then reduce the closed loop gain. Now, let us see what is the error in the output, what is the problem because of this output resistance, because we have to remember that if I have a op amp circuit, then if I am loading it, if I am loading it, if I have the load, then if I change this, then I can this output voltage will be changing. How much it will be changing? That will be R 0 into delta I, that is the change that one should look at this point. This is an uncompensated error. This is after compensation, this is the change that is accepted. So, we write that this is a change, this is the delta is this is change after compensation, after after compensation. After compensation, this is the change that is expected in the op amp terminal. So, one can find out what is R 0 from the manufacturer data sheet, because R 0 can be find out by the actual R value is given by the manufacturer in the data sheet. In the data sheet. So, once that is known, then closed loop gain and open loop gain also closed loop gain you will know, and open loop gain also we can find from the data sheet, and then one can find out the output resistance. And once output resistance R 0 is known, one can find out the what is delta I, and then multiplication of that gives you the actual output voltage change. Now, this error is to be taken into consideration in addition to the other errors that we have discussed. The other errors that we have discussed is what is the bias current error, then what is the input resistance error, what is the gain drift error, all that to be considered in this case. Now, one more aspect is that this current that is flowing here through the feedback resistance also comes from the output. So, if I put this resistance, so this also load for the output only. So, feedback resistance, because we had originally started by assuming RF is large, but in actual case RF also acts as a load for the op amp. In real use, in real life, real case, RF also acts as a load. So, if RF is small, then output resistance also if RF is small, then output voltage will decrease, output voltage will decrease. That is why we should not use small low value of RF. If we use low value of RF, then output resistance output resistance induced error will increase. So, for that's so one should not use low value of RF, particularly low value of RF is tempting, because if I use a low value of for RF, bias current error will be small. Should not use low value RF because low value of okay, should not use a low value of RF. Low value of RF reduces the bias current error, but it will increase the output resistance related error. Normally one cannot take more than 10 milliampere current even if you put too low value of output resistance. So, normally the output related error is somewhat related, somewhat less only compared to the bias current error, because one cannot take more than 10 milliampere current from the output of the most of the op amps. Some op amps are capable of giving up to 20 milliampere, but nevertheless you cannot take too much current from the output of the op amp. It should be noted that output current should be noted that normally there is an internal limit, there is a internal current limit for every op amp. For most of the op amps, the output current is limited to 10 milliampere. Most of the op amps output I is limited to 10 milliamps. So, normally the output related error is not very high compared to the bias current error. So, normally bias current limited error is much more than the output current. Bias current error, introduced error, bias current related error much larger than output resistance related error. So, normally we are not much worried about the output resistance error, but in some cases when the current drawn is much larger, then this error is a problem. For example, if I want to load heavily at the output, then since the current also limited, so normally what we do is we will bias this, we reduce the output current using the transistor. For example, if I need a very high current, the normal practice is that you take the op amp and put a transistor. For example, I can have this arrangement, then return the emitter to this. And give the input to this. So, you have the transistor T1 and then your load can be now very high. This is load. For example, the HFE of the transistor is 100. Assume for HFE for beta of the transistor be 100. If beta is 100, then we know that load current, this current I and this current output current of the op amp related by beta. So, I by 100. So, for load current of I, then the output current of the op amp is very small, 100 times lower. So, now the output voltage error we have to compute only for this reduced current, not for this current. For example, if I have a 1 ampere current here and if HFP is 100, then you will have only 10 milliampere current, which the operational amplifier can give. So, we have to compute the output current error only for 10 milliampere. And remember that we have taken a feedback from the output here. You should not take a feedback from this to this. For example, I should not connect in the following manner, then you will not get the correct voltage. like plus 15, connect this, connect the input V input RF R1. Now, this is if we are taking this output, then this RF should not be the gain RF by R1, this resistance should not be connected here. So, this circuit is wrong, this connection is wrong, this is not acceptable. So, if you want to boost the current, the resistance the RF must be terminated to this point, to the output, not to the output of the op amp, that is terminate this resistance to the output, not to the output here, but to the output. So, what is normally done is you connect this one to here, this is okay, but this is not acceptable. So, one have to because once you connect this resistance here, that is if I connect this here, the base emitter voltage change, the anyway base current will be very small only, because the loading effect is very small, because this base current is small, because the HFE of the transistor takes care most of the current, and most of the current is coming from here, and the base current is small. But nevertheless, the base emitter voltage change, which is 0.6, that is not compensated by the closed loop, because this 0.6 voltage loss will be there if this is connected. So, base emitter voltage drop will be a loss. VBE is a loss, and this also the VBE changes with temperature, VBE changes is a loss, and VBE changes with temperature. That is why one should not connect like this. So, if you want to connect, then connect the RF directly to the output. Now, this actually we can see even in the our voltage regulator circuit, which we had seen, is a type of output resistance reduction circuit only, because we can see if you look at the voltage regulator circuit, we will get like this, that is we have a unregulated voltage here, then we will connect the op amp circuit. In fact, we put at Arlington if you want very high current. So, we connected this, then connected this here. So, we are connected the output of that to this. For example, I connect this here. This is a, we call this a voltage regulator, this is V reference, and we have discussed already this one. This is a voltage regulator circuit, voltage regulator. Actually, it is not a voltage regulator. It can also be considered as, it can also be considered as non-inverting amplifier. Because you see, if I look at it, I do not see it as a voltage regulator. If I see as a non-inverting amplifier, what actually happens? We, you see, we instead of calling V reference, we call it as the input voltage, and these two are feedback resistance, that I call it as RF and R1, feedback resistance. So, this voltage, whatever you are giving input voltage, is multiplied by this RF by R1 plus RF by R1 is what appears at the output. So, V output, I can write it as V output is equal to VR into 1 plus RF by R1. So, this is acting as a gain, and reference acting as a input voltage. reference is acting as a input voltage. So, the input I can call this is a voltage regulator is nothing but an inverting amplifier with low output resistance, that is output resistance reduced by using the Darlington pair. So, here Darlington pair acts as a output impedance reduction, output resistance reduction. And also to boost the current, because op-amp cannot give too much current, it cannot give more than 10 milliampere current. So, this multiplied by beta is what the output current comes. So, I can say this is a inverting non-inverting amplifier with low output resistance. So, it is a non-inverting amplifier with low output resistance. Now, assume that what is the output resistance of the of this circuit. So, if I have here for example 10 milliampere current, then if I have 100 ohm resistance here, then one can expect 1 volt drop across this, or I can say the output at the op-amp output, what is the resistance, what is the output resistance at the output of the op-amp, at the output of the op-amp, the we can write R 0 into I, that is 10 milliampere, is the change, is the expected change. Now, for example, typical case, if I take what is the R 0, R 0 actually in this case is 100 ohms, and then we have a closed loop gain and open loop gain. If we calculate, for example, if I have in this case, if I take at this point, then I say that it is a open loop circuit, or if I take this as my output, that is what we are doing, then this can be taken as a reason. Suppose if they are equal, then the gain is actually closed loop gain is 1. So, in that case 1 plus 1 2. So, the output resistance becomes 2 by 20,000, that actually become 200 by 20,000, which actually because 1 by 100, that is 10 milliohms. So, output resistance will be 10 milliohms, and then at the output of the op-amp, then we can expect 10 milliohm into 10 milliampere current, that is 100 microvolt change expected because of the output resistance itself. Of course, the output voltage change here are due to many other reasons, that is when normally when you make a voltage regulator, instead of the battery we will feed a unregulated voltage, then this voltage itself drops with the load current, then the supply voltage also changes, then the current flowing through this changes, all that contributes for output voltage regulation. So, which we already discussed earlier, which we need not repeat it here. So, the voltage regulator circuit what you are seeing is a kind of circuit which actually is having a reduced output resistance circuit, is nothing and no need to be called as a voltage regulator. It is only a question of how we look at the circuit and a different angle. So, what is the other effects of output resistance? For example, sometimes you will connect the circuit like this. For example, if I have a operational amplifier circuit, now I give the input, assume I have a load here, which is assume it is quite low. I am not using any this thing, that is any transistor to boost the current. So, this is a load, then I put the resistance here, this one. The other resistance I can do like this, I can connect it to this point, then I can also connect it to this. Other way of doing this would be here itself I draw that is I can connect this way. I can connect it this way, say I can have a load, have this, then connect this at this point. Now compare these two circuits. If I take these two circuits, this is a good circuit, this is the practice to be followed, this should not be followed. The reason is, if you look at this, that this voltage drop, the current that is flowing here, this has a resistance R and the current I is flowing, the load current is I very substantial, then there is a voltage drop of R into I. This R into I also compensated by the closed loop action, that feedback action compensates this loss to the extent R into I by AD into G. So, that is not there in this case. For example, here you have a voltage, this voltage loss is not taken care, voltage loss is not taken care. So, one have to use only this type of circuit in the actual usage. So, the actually the I will call this A and B. So, voltage loss between A and B is taken care, voltage drop between A and B is taken care in this circuit. It is not taken care in this circuit, not taken care. So, the first circuit only to be used for this purpose. We will close this discussion with this. We will see in the next class the consolidated application of all these errors and then we move on to the AC applications. Thank you.